engineers at how we measure these things, what do we look at? And one thing is our hydrograph, which is a graphical representation of how the stream or the flow responds after a rain event. So you can see on this graph, if we had the rainfall there represented by the red bars, when the rain falls, the stream is going to have more flow come into it, it's going to go up, and then it tend to rise pretty fast, and then it declines a little more slowly over time. So we use this to design detention systems, we use it to design storm sewer pipes, and the peak discharge, if I start talking about peak discharge, that's the top of the curve. So the point where it's the highest on the curve is the highest flow, so that's peak discharge. And another example of this that Mike Perez has developed, you can see for an urban stream, what you might see is the rainfall at the top. It's kind of a reverse graph where he's got rainfall on the right and you've got stream flow on the left. This is probably for a larger stream because you can see the stream flows in the thousands of cubic feet per second, so it's very, very large. But you can still see some of these representations where you have a rainfall that happens and then the stream flow goes up. And there's going to be a lag between those two. There's a delay between when the rain falls and how long it takes to get to the stream or wherever you're looking at. And in the rural areas, or even before we had agriculture in the natural environment, that lag would have been really, really long. It may have been hours, and then as agricultural developed, it got to probably an hour or less than an hour in some of our smaller watersheds. And then as we start to get into the urban environment without detention and other things like that, that can start to really get down to like far less than an hour, or maybe even minutes in some cases. So that lag, that response keeps narrowing down. And you can see some of those effects on these graphs that he prepared, where this was in a case study in Ankeny where they looked at a tributary watershed that is about 200 acres. It had a little more than 40% impervious cover in it. And you can see what would have happened naturally even before agriculture is the red graph way down to the bottom. As we start to go into agricultural development, you can see where the blue curve is, and the peak is moving to the left on the graph, so it's happening earlier, and the peak is taller. So we have a higher peak flow, and we have more volume. And then after development in this area, you can see that it's much, much higher. This is for a one-year storm event. So again, about 2.6, 2.7 inches of rain, so not a very huge event, but you can see these big changes in why we have to kind of manage for this event. So, if you didn't do anything, if you just let it run off the site, you're talking about a peak flow rate from the bottom to the top that's about 15-fold, and then the volume's up about 4 times. So that's kind of what we're trying to avoid, because the result of that is what we've seen play out across the nation. They've done some studies through the Center for Watershed Protection where they mapped over time different cross-sections of streams. And you can see the historic cross-section before development was the lightest blue, and then over the years they'd come back and remap it, and eventually it was a much larger stream. It would downcut over time, it would widen out, and it gets bigger. And you can see this is kind of those steps in that evolution. So you start where it starts to incise, which means it downcuts. It starts to cut to a narrow little channel. You may see this on construction sites where it starts to, you get a rill or a gully that forms where there's some point discharge. But that can happen in streams too. They may not be very defined at first, but then pretty soon there's kind of a little cut in the ground that starts to deepen. And then as it gets deepened, it starts to widen out. Eventually it widens out to the point the sides are really steep, and they'll start to fall in, they'll start to cave in because they become too steep. And then you start to kind of get this even wider section, and eventually it kind of finds a little flow path that it likes at the bottom. So you see this kind of progression over time, and it may take decades for this really to play out. But you go from before anything was going on to the final cross-section. You can see how much lower and bigger it can be. And they were able to measure this and relate it to the impervious cover in the watershed. So this is on the left, you can see this is enlargement ratio. So that's how much bigger it was compared to the original size of the channel. So a ratio of 1 would mean it's the exact same size that it used to be. If it's a ratio of 2, it means it's twice as big as it used to be. And you can see that as they graphed this, that they got to about watersheds with only about 20% impervious cover, were typically about twice as big as they were before development. You start to get up to 30 or 40%. A lot of our single-family residential subdivisions probably are getting close to 40% impervious cover. So, we're not talking commercial corridors here. We're talking single-family residential. They were seeing a larger ratio of about 4 to 1. And then as you start to go even higher, you can see even the curve starts to sweep up. So obviously there's some documented cases and some relationships where they've seen this play out. And the reason for it, like if this is kind of like our existing flow rate and we're just managing to that, or even if we're not detaining it at all, we're much, much higher than what a natural rate would be. So the goal of the channel protection volume is to kind of mimic more of the red line, to be more like what the natural condition would be. So, we're talking, like graph I showed earlier from Mike Perez, where we had that big jump. We're trying to avoid that big jump. And if we didn't do that, if we just kind of like tried to match what happens like in the ag environment, what would happen? Well, even if we detained it, by matching this peak, you can see some of these flow rates that maybe would happen for a half hour at a time or an hour at a time. Well, now they're lasting even longer. So we might see that this flow here, instead of half an hour, it might last an hour. Or this flow here, instead of lasting an hour in length, it might last 3 hours. Because we're adding another 2 hours to the back of the hydrograph. So if that channel is going to erode at 10 or 20 or 30 CFS, now it's not only seeing that much more volume, but it's seeing it for a lot longer, for several hours, where it may have only seen it for a few minutes before. So that's where we see not only the instability because of the jump in flow, but because the stream's seeing that higher level of flow for a lot longer. So that's where that kind of going back to this approach is preferred as far as maintaining the stability of the downstream channel. So this is what we're trying to basically kind of avoid. So that's the goals. What does it take to do that? That's it sounds important. What does it take to do that? Well, you can build this in, and I'll show you an example in a little while when we talk about multi-stage outlet design. This feature can be built into a lot of detention ponds and wetlands and things that we already do today, where we can modify the outlet to achieve these goals. In order to do it, the target result on inflow to outflow is usually about 95 to 98%, somewhere in that range. And you may think, well, that sounds like a lot. But really, to achieve that goal, you need to store about 55 to 65% of the rainfall. And that, again, depends on how much impervious cover you have in your watershed. But it ends up only being about 1.5 to 1.7 inches. So we were talking earlier having to manage about 1 inch for the water quality volume. Well, now you're talking about 1.5 inches or 1 3/4 to do something that seems to be pretty important from the kind of hydrograph math side of the equation. Okay, so that's kind of the small storm piece. Before I go on to the large storms, does anyone have any urgent questions about some of the small storm runoff management? Or my nice tone of voice and post-lunch time frame put everybody to sleep already? Okay, we'll keep going. So the large storms, what did I just do? Here we go. Hit a key to zoom there. The large storm events. Now we start to get in a lot of the small storm stuff. There are a lot of places that have done it, but it's probably the part of the equation that's the least familiar to some people. Because we've been managing for large storms in one way or another for a long time. I mean, going back 30 or 40 years, there have been ways we've been trying to provide detention for these larger storm events. So it's not really new, but it's just a little different. There are really 2 levels in ISWIM for the large storm management. One of them is called the overbank flood protection, and one is called the extreme flood protection. And the overbank flood protection is named because it's supposed to do just that. It's supposed to reduce the amount of overbank flooding we see in our urban streams. And it's also targeted towards preventing our storm sewer systems from being overwhelmed, from them surcharging. So that's why, you know, we talk about this, it goes up to about the 5 or the 10-year level, probably depending on what your local community uses to size the storm sewer system. If they use the 5-year, that's kind of the cutoff. If some communities have gone to using a 10-year, then that's kind of the cutoff. So that really the purpose is we're detaining that water, so as it goes downstream, it's not going to overwhelm the storm system. Now, the release rates that are prescribed in the ISWIM manual are based on that kind of natural condition, or meadow. And the reason for that is because we still are, like I mentioned earlier, you're still letting more water go. You know, it's not an even like, hey, let's match existing flow and existing volume. You're letting more volume go. So first thing is we're trying to trade off that effect and minimize downstream impacts. We got more water going out, we need to reduce the peak rate a little bit. The second part is a lot of our streams and our floodplains, you know, the natural condition was a much more stable condition. So that's one reason why that's used as a standard. So if you implemented this in an area that's developing, what you should see over time is that the peak flow rate should actually go down. Overall flow volume is going to go up. But hopefully you're making the peak flow rate go down enough that you're reducing impacts from flooding and things like that. Another benefit of having it go down is reducing the potential for peak matching. And what that is when I showed you the graph earlier of the hydrographs, and I probably should have pasted it here too. Sometimes what can happen when you design a bunch of detention basins in one neighborhood, if you're letting the water go at the rate it does today before development, and all those basins let their water go about the same time, these peaks can line up in ways that maybe they didn't originally. You know, the water from one basin downstream might let it go a little more slowly than it did before, and all of a sudden all the water is getting let go down the corridor at the same time. So there's part of ISWIM that talks about downstream hydraulic analysis that looks at that, but if everybody's letting their water go about where it is today, you have a greater risk of that happening where these peaks line up. If we're at that more natural level and everybody's lowering that, the chances of that causing a problem is a lot less. Even if people are letting the water go about the same time, you're letting it go at a lower rate, so the risk of it being a higher flow rate than what was before is minimized. So those are the potential benefits of that standard. And to achieve that, you don't have to reduce their flow rate as much as you did for channel protection volume. It depends on, again, the watershed characteristics, but you're usually running somewhere between 65 and 95% flow reduction. Most of it's probably in that 65 to 75% range. And you're having to store a lot less of the runoff to accomplish that. You're talking about 35 to 60%. So, you know, again, anywhere from 1.6 on a lighter developed area towards, if it was more of a commercial corridor that's maybe 70 or 80% impervious, you might be up at that 2 3/4 range of trying to meet this standard. And then finally we get to the biggest teardrop, and depending on how you can do it, how you're asking for it to be done, this can be the most expensive, but the way that it's structured is we're trying to have it not be. Because we're not asking you again to retain that volume. If we were to ask that you were going to retain the increase in flow at the 100-year level, that would be a very, very expensive thing to do. So this is just focusing again about rate control. So you're trying to reduce that outflow rate from the basin during a 100-year storm event. And the goals are to reduce downstream damage of property and infrastructure, providing flow control, releasing that rate again, kind of that more natural condition, so we're reducing the outflow rates. But I should say, some communities, as they've adopted ISWIM, have chosen to also limit the release rate. They look at that 100-year natural condition, but then they also look at what's called the 5-year pre-developed rate. So they look at it like agricultural 5-year rate, and they see which one's lower. And they say, well, whichever one's lower, we want you to meet that. And part of the reason why some communities have done that is a lot of our detention ordinances have been written that way for a long time, where it's the 100-year developed is the 5-year pre-developed, 100-year in, 5-year pre-developed out. So they've kind of stayed with that. And there is language in ISWIM that kind of says cities can choose to adopt that, but that's kind of not the default position. you could, or we as a group could say, yeah, we want to use that because it does protect the downstream storm sewers from even these big events. But in some communities have said, hey, this is a spot that if we're asking them to do more on the low end of the spectrum for water quality, maybe we can give a little relief on the high end of the spectrum here. So if you don't have that clause in there, you can actually like increase the flow rate a little bit during the 100 year. And again, this is a pretty rare event, so that's one thing to keep in mind. But there may be some circumstances where you don't want to do that. There may be downstream restrictions that you're concerned about, or there might be downstream flooding that you're trying to reduce the flow rate as much as possible. So you could put this restriction in there either on a community-wide level, or you could say maybe there's certain sub-watersheds, or there's certain direction given to city staff on where to implement this higher standard. So I guess the main point I'm trying to make is there's some options on what you do with this. But if you just kind of stay with the 100-year natural condition, it might actually be a little bit higher release rate than what was previously allowed. The goal is to mimic natural hydrology. And again, if we're reducing that flow rate from existing, we're reducing that potential for peak matching of the downstream basins. But just to